Hello again. In this video, I am going to show you how to derive the weak forms in the finite element method using the weighted residual method. Weak forms are one of the important concepts in finite element method. Okay, so that's why it's important to know how to derive them for different problems, starting from the governing PDEs. Okay, so first let's have a look at a very simple problem. We consider a scalar field problem in 1D, that is, there is only one variable, for example, a Poisson equation. Or, okay, or we can have a simple like bar example if you talk about elasticity problems. Okay, so let's take this 1D example. Okay, so we have a domain starting from HL and ending at HR, okay, left and right, okay, and X coordinates. And our solution variable is U, and U is fixed, and U has a specified value of 0, that is homogeneous Dirichlet boundary condition at X equal to HL. And there is a load. Okay, if you talk about elasticity, there is a force of P at HR. Okay, so we have a Dirichlet boundary condition, and then there is a Neumann boundary condition. Okay, so for this problem, the governing PDE is this simple minus mu dou square u by dou x square equal to F. Here U is our variable, solution variable. Like for example, here U is the displacement in that direction, and mu is a material parameter. So for example, it happens to be EA. E multiplied by E is N's modulus, A is area, but it's not really important now. So mu is a material parameter and F is the source term. So as I said, the domain H starts at HL and ends at HR. L for left, R for right. This is our PDE, and we are provided with the boundary conditions, that is the solution is 0 at the left end, and we have a value of P at the force at the right end, and this P is the Neumann boundary condition, so which becomes mu dou u by dou x at x equal to x r equal to P. Okay, so using this information, we are going to derive the weak form for this problem. Okay, so first we start with the residual of the PDE. We know the PDE, we write the residual. Residual is nothing but we take all the terms to the one side. That is, we take all the terms from the right hand side to the left hand side. So F becomes minus F. So we have the residual. And then we have the weighted residual statement. So what is the weighted residual statement? Weighted residual statement is the integral of the weight function W multiplied by the residual, okay, integrated over the domain, whole domain, that is, okay, integral is equal to the 0. This is the average. So we have the weight, so we are averaging over the whole domain. Okay, so the dot product of the weight function W and the residual are integrated over the whole domain. This is the weighted residual statement, and this is equal to 0. This should be equal to 0. There are various ways to think about it. That is, we are projecting the residual and the weighted and the weight function space. Okay, so and that projection should be equal to 0, or other thing is the residual should be orthogonal to the weight space W. So that product is equal to 0 means they are orthogonal, right? Okay. So here in this problem we have W and R as scalars. Here the dot product doesn't make much of a sense because both are scalars, but when we go to vector field problems like fluid flow, like when we deal with Stokes equations or Navier-Stokes equation, or for linear velocity problems in 2 and 3 dimensions, then we have a vector field problem. Then there the dot product becomes very important. Okay, so this is the weighted residual statement. Weight function multiplied by the residual of the PDE integrated over the whole domain should be equal to 0. Now next we are going to replace R and then split the integral. Okay, so we have two integrals, so one on the left side and one on the right side. On the right side we have integral of w multiplied by f dx. So I just removed the dot product because w and f both are scalars. And here on the left side we have our PDE. Okay, the left side of the PDE minus mu dou square by dou square, this multiplied by w. Okay, so this integral. Next, now here if you notice here, so in order to approximate u, okay, we need to have an approximation for u that is square that is way that has non-zero second order derivative. Okay, so if we approximate u, then it should be such that its second derivative is non-zero. Otherwise, if it is 0, then the integral becomes 0, then we won't be able to do anything. So having an approximation that gives us non-zero second order derivative is quite difficult. Okay, so what we do is we are going to transfer one derivative. We have two derivatives on u. We are going to transfer one derivative from u to w. So in that way, we are going to weaken the derivative on u. Okay, so how do we do this? We do this by taking by using the derivative of product rule. Okay, what is the derivative of product rule? So we have two functions w and dou u by dx. Okay, so this is the product of w and dou u by dx, and its derivative is, so we apply the derivative to each, and then we have summation. Okay, dou w by dou x, dou u by dou x plus w multiplied by dou square by dou x square. Okay, so this is the derivative of product rule, and we assume that mu is a constant. Okay, it need not be a constant. Let's for the time being, let's assume that mu is a constant. Okay, so we place mu in this formula, in this derivative of product formula, so it doesn't change, it doesn't affect anything. Okay, so mu is a constant. So now we have the derivative of product rule including mu. Now what we need is this term. Okay, this term is the second term on the right hand side. Okay, now from this equation, from the derivative of product rule, we are going to replace this term in the integral with these two terms. So we take this to the other side, it becomes minus, and when we substitute this and minus of this into this equation and then simplify, okay, we get this expression. Okay, so this comes to the right hand side, it becomes minus, and we already have minus here, so minus plus minus, so this integral, and then minus of this integrated over the domain. On the right hand side we have integral w of dx. Okay, and then we start from here. Okay, so we start from here, and then we use the divergence theorem. What is the divergence theorem? According to the divergence theorem, the divergence of a vector field f integrated over the whole domain, the volume integral here, okay, is equal to the surface integral of the same vector field and its dot product of, okay, by the normal. Okay, the dot product of the integral, the dot product of the vector field f with the outward normal n integrated along the boundary. Okay, when we simplify to 1D problem, so what we have? So we have only one dimension, x dimension. So the dot product becomes dou by dou x of fx. Fx is the x component. So and our domain is x. And then on the right hand side we have the dot product of f and n. We have only one component, fx and nx. So fx and nx, and the boundaries are xl and xr. Okay, so this is the divergence theorem, and we are going to make use of this divergence theorem in the second term on the left hand side. Okay, so now this integral becomes just application of the limits, upper and lower limits. Okay, so here, upper and lower limits for this term inside the bracket. So W mu dou u by dou x multiplied by nh. So this term is our extractant of the vector f, okay, multiplied by nh. So we have the limits hl and hl. The other terms remain. Okay. Now let's apply these limits. We apply the limit. So first we apply the upper limit. So we have minus minus and then the lower limit. So we get another minus when we apply the lower limit. So minus minus plus. Okay. So we have split this second term into two, upper and lower limits. Now we know for a fact about the normal, outward pointing normal to the domain. This is our domain. These are our boundaries of the domain hl and hr, and at the boundaries we know the value of the outward pointing normal. That is, at the right end the outward pointing normal has a value of 1. At the left end it has a value of -1. So we then substitute nh at both right and left ends. Okay. So for the right end we have nh as +1, at the left end we have nh as -1. Okay. So let's start from that point. Okay. So we start from here after substituting the normal. Okay. So what we are doing now is we are splitting this value, that is, so where we are evaluating this function, we are splitting it between these different expressions. So we split. So we have w. So we evaluate w at x equal to hr, and then we evaluate mu dou u by dou x at x equal to hr. Okay. Similarly, so we evaluate w at x equal to hl, and then we have minus here. So we evaluate minus mu dou u by dou x at x equal to hl. So these two are the boundary terms. Okay. Next, we are going to make use of the boundary conditions specified. That is, Dirichlet boundary condition on the left end and the Neumann boundary condition on the right end. Okay. So first we look at the Dirichlet boundary condition u equal to 0. This is a homogeneous Dirichlet boundary condition. So to satisfy this, we take the weight function or the test function w such that it belongs in the H01 space. This is a Sobolev space. I will explain a little bit in more detail about the spaces later. Okay. So we take the w in this H10 space. So we see what this space means. So in this space, so the w is such that it vanishes on the Dirichlet boundary. Okay. So on the left end where we have a 0 boundary condition, that is homogeneous boundary condition, the test function vanishes. So this term on the left boundary becomes 0. And next we use the term on the right side boundary, that is p. Okay. And this term on the right side boundary, which is mu dou u by dou x at x equal to hr. So this term in the brackets is p at x equal to hr. So by removing this term and by replacing this with p, we have, so the first term, integral of mu dou u by dou x, sorry, dou w by dou x and dou u by dou x dx equal to this term due to the force, the source term, and then from here, okay, w at x equal to hr, that is the weight function at x equal to hr multiplied by the specified value of the p. Okay, so this is the weight form in one dimension. Okay. Now if you notice here, so as I said, we transferred one derivative from the PDE, that is, from instead of dou square u by dou x square, now we have only dou u by dou x, and that derivative we have transferred it to w. Now instead of w we have dou w by dou x. So in this way we are weakening the requirements on the basis functions that we need to approximate the solution field u. Instead of needing a spaces for which not only the value but also its derivative need to be continuous. This is what we call as C1 continuous elements. Instead of that, now we have only the value to be continuous. We don't need the derivatives to be continuous. So by weakening the derivative, we can employ a piecewise continuous polynomials as basis functions, that is C0 polynomials. Now, this is for 1D problem. We can generalize it to 2D and 3D problems. But before we go into the 2D and 3D problems, let's have a brief look at the function spaces. So L2 space. What is an L2 space? L2 space is a space of square integrable functions and the integral is bounded. So what does this mean? Okay, so it is a space like with V as its member. Okay, so the square integrable means the square of that V, the member, integrated over the whole domain omega, that should be bounded. That means the integral should be less than infinity. It should be bounded. It should be a finite value. This is the L2 space. And the HK space. So this is a space of all integrable functions V. Okay, we have all the functions V defined on the domain omega, and with the properties such that not only V but also its partial derivatives up to order k belong in the L2 space. Okay, so both V and its and the derivative of V up to order k belong in the L2 space, and this HK space is a Sobolev space. For example, we need H1 space. Okay, so H1 in the H1 space, the function V, it belongs in the L2 space. Also, its first derivatives, like if you look at 3D, so first derivative dou v by dou x, dou v by dou y, dou v by dou z. So all the first derivatives also belong in the L2 space. This is the H1 space. If you have H2 space, then the second derivatives should also be in the L2 space. Okay. And the third one is HK0 space. This is the H1 space but with some restrictions. Okay, so HK0 space is a subspace of HK space with the restriction that the function V is 0 on the boundary of the domain. Okay, so we take the HK space and we limit that function to be 0 on the boundary of the space. So this is the HK0 space. So we need this space for solving problems with homogeneous Dirichlet boundary condition. So this topic of function spaces is quite complicated. So if you find it difficult, you can skip it. And if you want more details, you can refer to the test books at the end of the video. Okay. Now let's look at the extension of the Witt form or derivation of the Witt form for the scalar field equations in 2D and 3D. Now this is the PDE for scalar field problem in 2D and 3D. So this is generalized equation. So here this nabla is the gradient operator. So del u means the gradient of u, and del dot is the divergence. Okay. And for example, if you are in a 2D domain, so we have a boundary conditions. So for simplicity, we assume some Dirichlet boundary condition like on some part of the domain where the solution is 0, and on other parts of the domain we can assume that there is a specified value of mu del u dot n. This is the normal kind of flux. Okay, it is specified on the boundary gamma n. Okay, now here like I said, nabla, this inverted triangle is nabla. This is a gradient operator. In 2D, it has two components, dou u by dou x, dou u by dou y. In 3D, we have additional component, dou u by dou z. So normally we take this gradient of u as a column vector. Okay. Now again, our procedure is the same. We start with the residual of the PDE and we write the weighted residual statement, which is the dot product of the weight function multiplied by the residual integrated over the whole domain should be equal to 0. Okay, so then we substitute the residual, we split the integral. Okay, we have one term on the left hand side and another term on the right hand side. Okay, and then we use the product rule again to split again this integral on the left hand side into two terms, with where one term is the boundary term. Okay, this way we apply the boundary conditions. Okay, now here we use the product rule, and here for the in the product rule we need a product rule where one value of the product, one component of the product is a vector. Here a is a vector, w is a scalar, w is our test function, and a is our mu del u. Okay, mu del u. Now, if you are using this product rule, okay, so we need w del dot a. Here w del dot a. Okay, so we take w del dot a, then we take this to the other side, and then we split the integral. Okay, then on the second term we have the divergence, so we make use of the divergence theorem. Okay, so again now we are in 3D, so divergence theorem we use as it is. Here our f is the term inside the bracket, so w mu del u, so it becomes, so f, this is our f, so f dot n, so f is w mu del u. Okay, so this is our boundary. So here we have transformed the volume integral into a surface integral over the boundary. Okay, so here the derivative, sorry, the integral, so this is dA not dV, because we are integrating along the boundary. Okay, so after this we apply the boundary conditions. Okay, so we have u is equal to 0 on the Dirichlet boundary, and we have this condition h specified on the Neumann boundary. Okay, first we split the boundary term into two, for the Dirichlet boundary and then for Neumann boundary. Okay, and then we assume that w is in h10 space. That means w is 0 on the Dirichlet boundary, so this term vanishes, and this term is h from the boundary conditions. So after simplification we have the weak form. So we write the statement like this. Okay, so for all w is in h10 space, find u, and u should also be in h10 space, because u should satisfy the condition that u is equal to 0 and the Dirichlet boundary. So we need h10 space such that this expression is fulfilled. So this is the first term, and once we replace this with h, this is our second term, and we take this to the right hand side because we know h, so it becomes plus. So plus integral over gamma n wh dA, and this term due to the source term f, okay, so it remains on the right hand side. We know f. So this is the weak form for the scalar field problem for homogeneous Dirichlet boundary conditions and non-homogeneous Neumann boundary conditions. Okay, but this is not all. We cannot solve all the problems using this weak form. Okay, but what about non-homogeneous Dirichlet boundary conditions? That is when the solution specified is not 0. Okay, so we see how we modify the weak form in order to accommodate the non-zero Dirichlet boundary conditions. Okay, our PDE remains the same, it doesn't change. And then in the boundary conditions, instead of u equal to 0, we have u equal to g. G is a function that we know. So using g, we can calculate u on the boundary. Okay, for the sake of derivation, let us assume that there are no Neumann boundary conditions. We have a pure Dirichlet boundary problem. Okay, again after applying the weighted residual statement, after applying the like product rule, and then using the Gauss divergence theorem, we get this weak form. Okay, now we still need the test functions in h10 space. However, if you do that, u cannot be in order to do that, U cannot be in the H10 space. If you select U from the H10 space, then U is going to be 0 on the boundary. However, we know that U is not 0 on the boundary, right? So it cannot satisfy the non-homogeneous Dirichlet boundary conditions on the boundary. So we fix this by a simple tweak. What we do to fix this, we assume that the solution field U is a linear is a combination of U bar and G. Okay, where U bar is the solution for the PDE satisfying U equal to 0. Okay, U bar is the solution for this PDE satisfying U equal to 0. That is, U bar is in the H10 space. That is, U bar is 0 on the Dirichlet boundary. And to U bar, we add G. G is again a space, a function space in H1 space. So, and G satisfies this condition, G, capital G equal to small g on the Dirichlet boundary. Now, from the given function G, we can discretize it and calculate capital G. And once we find the solution U bar such that it is 0 on the boundary, okay, so then we add U bar and G, we get the solution for this PDE satisfying this boundary condition. Okay, it is a small tweak, but this is what makes it powerful. Now, by making use of U equal to U bar plus G, we write this weak form. Okay, so again, instead of U, we have U bar. We solve for U bar such that U bar equal to 0 under Dirichlet boundary. So we remove that term, okay, after we apply the divergence theorem. Okay, here if we substitute U equal to U bar plus G, then we have U bar here, and then the G term will go to the right hand side, so it becomes minus of this. Okay, so this is our weak form. Okay, so now by extending this to a general problem where we also have the Riemann boundary condition, so our weak form becomes, so for all W, for all the weight functions in the H10 space, find U equal to U bar plus G with U bar in the H10 space, that is, it satisfies the homogeneous Dirichlet boundary conditions, and G in the H1 space. It is not H10 space, it is H1 space because it should not be 0 on the boundary. Satisfying capital G equal to small g on the Dirichlet boundary such that this integral expression is satisfied. Okay, so if we have homogeneous Dirichlet boundary condition, then capital G is 0, so this term vanishes, and then our U becomes U bar. Okay, so for non-homogeneous Dirichlet boundaries, so we have an extra term. Okay, so this is how we derive the weak form for problems with non-homogeneous Dirichlet boundary conditions. Okay, so what is this extra term? How do we deal with it in programming? For example, if you are interested, okay, so just briefly. So this extra term, so we are subtracting it from the right hand side. If you haven't noticed, okay, so like if you write it like this, after discretization, we have Ku equal to F, and this extra term is, it's very similar to K. Like if you notice, the only difference is U bar and G, right? So if this is K after discretization, then this is also K after discretization. And then we have capital G corresponding to the discretization of the degrees of freedom, or the solution values of nodes, okay, corresponding to G. Now, okay, so for example, if you take a problem here, this problem, okay, four elements, 5 nodes, and we know U1 and U5, they are specified. Okay, so now after calculating the stiffness matrix, this is the expression. and before applying this boundary condition. So this k is the same on both sides. And here we know u1 and u5. Okay. Now, since we have only u1 and u5, we can simplify this by multiplying the corresponding columns with the u1 and u5. So this is what this extra term corresponds to. So if you have followed my first video on implementing the finite element method in MATLAB for the 1D problem, and this is what we did, and this the mathematics behind this is this. Okay, so this is from the weak form. We can extend this further for problems with anisotropic material. Now, so far we have assumed that mu is a constant, but mu need not be a constant. Like constant in the sense this is isotropic. Like mu is the same in all the directions. What if mu is anisotropic? In order to extend the weak form to problems where mu is anisotropic, we made again some minor modifications. We represent the weak form in the matrix vector notation. So this makes it easier to apply the discretization. So again, okay, this is our weak form. We have derived this, okay, and we know that del u is this. Okay, so I am writing it here just because we are using dot product. Okay, so del u is a vector. So when we have dot product, it doesn't really matter how we write. Okay, so we have a vector multiple, and then another vector. We are taking the dot product. Okay, but if you want to write it in matrix form, we need to be careful about whether a term like del u, del w, whether it is a row vector or column vector. Okay, so if you remember from our previous discussion, we have del u as column vector. Okay, and by noticing that we have a dot product here, so del u is a column vector or a column matrix. Del w is also a column matrix, column vector. Okay, right? Now, if you multiply, if you take this dot product, we have a scalar value. So in order to get a scalar value using matrices, we need to take transposes. Okay. So del u is a column vector, del w is a column vector. In order to multiply them and get a scalar value, we need to take the transpose of del u, del w. Okay. So this is the transpose of del w. This is del u. Okay. So that means so in the matrix vector form, we have del w transpose multiplied by del u. Now here on the right hand side, there is no change because they are just scalars. Now, what is the advantage of writing this? So the advantage is after we discretize, that is like we take the approximation for u. So this here any the matrix of basis functions, and u is the vector of degrees of freedom. Similarly for w, and then we have the gradient for u, del u, then gradient for w. Okay. Well, once we substitute them here and like get rid of all the other terms. Okay, so just bear with me. So we should have u here. Okay, so now by writing this in a matrix vector form, it's easier for us to write the discretized form. Okay, so there is a reason why I have put mu inside G transpose G. Okay, so the reason is like we can easily extend it to anisotropic problems. For example, for anisotropic material, okay, the PDE looks more or less the same, except that this mu is not a constant anymore. It is a tensor of order 2. Okay, so okay, for anisotropic materials in 3 dimensions, so we have mu as a tensor of order 2. So that means we have a 3 by 3 matrix. Okay, so now we draw back to with form. So here again mu is in bold, so representing, like identifying that it is a tensor, it is not a scalar. Okay, now so by replacing the dot product and by using the matrix vector notation, now we have del w transpose mu del u. Okay, now this makes sense in terms of the dimensions. For example, del u transpose is 1 by 3, mu is 3 by 3, and del u is 3 by 1. So 1 by 3, 3 by 3, 3 by 1. We get 1 by 1, which should be a scalar. Okay, so this is the beauty of writing it in the matrix vector form. Now after discretization, okay, so now if this is the expansion form, now after discretization again we have in the same expression. Okay, so G transpose mu G again. Okay, so notice the error. Okay. Now similarly we can extend, like we can derive the weak form for linearity. So for the linearity, this is our governing PDE. So here sigma is the Cauchy stress tensor and Fa is the body force, like the gravity, and we have the boundary condition, the homogeneous boundary condition, that is a fixed support on the Dirichlet boundary and a specified traction on the Neumann boundary. And we start with the weighted residual statement. So here weight and the dot product of weight with the residual R. R is like F, we take it to the left hand side, so minus del dot sigma minus F, and note the difference here, R is a vector, that is why it is in bold. Okay, and W is also bold, the representing that it is also a vector. So in 3D we have three components, X displacement, Y displacement, and Z displacement. That is why we need the dot product here. So but W is a vector and R is a vector, so we need the dot product. So that is why dot is important. And then we substitute for R. Okay, and then we split the integral, we have this expression. Okay, next we take the product rule and then apply the divergence theorem. So if we apply, we get this expression here. This double colon is the contraction operator. Here sigma is a tensor, is the second order tensor, and del w, here w is a vector and del w becomes again a second order tensor. Okay, since we have tensors, we need the contraction operator. This is like a dot product but for second order tensors. So that means when we evaluate this term, that is del w, this contraction operator and sigma, we get a scalar. Okay, and this is our boundary term, and okay, by replacing sigma dot n equal to h on the Neumann boundary, we get w dot h. And again note that h is the vector here, that is why we need to keep the dots. Okay, dot products are important. And we can write this using epsilon. Now we notice that sigma is a second order symmetric tensor. So we, instead of del w, we can have a symmetric form. Okay, so epsilon, which is a small strain tensor. So small size tensor is the half of del w plus del w transpose, and that makes it symmetric. Okay, so epsilon. So instead of del w double colon sigma, we have epsilon. Instead of w, we have epsilon, and this doesn't change anything here. Okay, and then using the matrix vector form, we use transposes. Notice that epsilon, okay, is again second order tensor. Okay, so for finite element representation, the matrix vector forms are quite useful. So epsilon transpose sigma, W transpose F, W transpose H. Okay. So this is how we derive the weak forms for different PDEs. I hope you found it useful. If anything is not clear, please post a comment. Okay. There is also a derivation for storage flow. So like if you want, you can try it on your own. And the only difference here is, the main difference here is that we have two equations in the storage flow. This is the momentum equation. Okay, this is the continuity equation. Which gives us the incompressibility constraint. So when we write the weighted residual statement, we need two weight functions. One is for the residual of the momentum, okay, and the other is for the continuity equation. Continuity equation del dot u is a scalar, so q is a scalar, and momentum equation is it's a vector. Okay, so w is a vector, and afterwards it's all the same. We don't need to apply any transformations, like we don't need to apply any divergence theorem or product rule on the divergence of the velocity. Okay, these are the steps. Like I'm leaving this here just for, like, in case you want to give it a go on our own. And for Navier-Stokes, it is like we just add the advection, like a convection term, and everything else remain the same. For Navier-Stokes, we have the extra term coming from the convection operator. That's it. Okay, like if you want more, follow this in more detail, so you can refer to these three classical textbooks. So these are really good ones for the introduction, for the introductory topics on finite element method, especially in deriving the weak forms and also about the spaces, the different spaces. Thank you.